Have you ever stopped to think about what's really happening inside your phone or your computer? I mean, way, way down at the most basic level of decision making. Well, it turns out it all comes down to a hidden language, a set of invisible rules that literally power our entire digital world. And today, we're going to pull back the curtain on that language, Boolean logic. But let's start with a story, and not a happy one. Back on a Friday in July 2022, the entire country of Canada just went offline. And the cause wasn't some huge cyber attack. Nope. It was a tiny logical error, a single instruction that didn't do what it was supposed to, and the result was an absolute catastrophe.
I mean, we're talking about a complete societal shutdown here. People couldn't call for an ambulance. Businesses couldn't take payments. The country's infrastructure just ground to a halt. This is exactly what happens when those invisible rules get broken. It shows you just how incredibly high the stakes are for getting this stuff right.
So yeah, that huge Canadian outage, that's our starting point. It is a massive, real-world example of a failure in logic. And we're about to unpack the exact principles that could have stopped it from ever happening. To really get what went wrong, we first have to understand the system itself. And that brings us to the surprisingly simple and kind of beautiful world of Boolean logic. Here's the most important thing to get your head around. At its absolute core, every single digital decision, no matter how complicated it seems, boils down to one of two states: true or false, yes or no, on or off. This simple binary choice is the absolute bedrock of all computing. You can think of it like this. All of these concepts are really just two sides of the very same coin. Whether we call it true or the number one or the on state, it's all the same thing. And on the flip side is false, zero, or off. Everything your computer does is built on this simple idea. Okay, so if this language only has two words, true and false, how in the world do you build anything useful? Well, you use a special kind of grammar. So let's meet the main characters in our story, the logic gates. First up, we've got the NOT gate. I like to call this one the rebel. It's the simplest of the bunch. It takes one input, and it just flips it. That's it. You give it a true, it spits out a false. You give it a false, it hands you back a true. This chart here, it's called a truth table, and just maps out every possible outcome. And for our little rebel, the NOT gate, it's a perfect inversion. 1 becomes 0, and 0 becomes 1. Simple as that. Next, we have the AND gate. This one is the picky one. See? The AND gate looks at two inputs, and it will only, and I mean only, give you a true output if input A and input B are both true. Anything less than that, the answer is a hard false. Its truth table really shows you just how strict it is. Look at that. Out of 4 possible combinations, only one gets a true output. If and only if both inputs are true, then the output is true. Everything else is false. As a total contrast, we have the OR gate, who I call the chill one. The OR gate is way more relaxed. It'll give you a true output if input A is true, or if input B is true, or hey, even if they both are. It's very inclusive. And you can see that laid-back nature right here in its truth table. The only possible way to get a false is if both inputs are false. Any little hint of a true in there makes the whole thing come out true. And finally, let's meet the XOR gate, or the exclusive one. Now, XOR stands for exclusive OR. It's kind of like the OR gate, but it has one very important condition. It only outputs true if the inputs are different from each other. And right here is where the key difference lies. Just look at that last point on this slide. For a regular OR gate, if both inputs are true, the output is still true. But for an XOR gate, when both inputs are true, the output flips to false. It's strictly one or the other, but not both. And this little distinction is incredibly important in computing. Okay, so we've met our cast of characters. We have the rebel, the picky one, the chill one. But how do we get from these super basic rules to, say, complex math? Well, let's connect those dots. Right? How on earth do you add numbers using only logic gates? It seems kind of impossible, but it's all done by chaining these gates together in really, really clever ways. So this circuit is called a half adder, and it combines 2 of our gates to do basic math. Now look at that last row. When both inputs are 1, the XOR gate gives us a sum of 0, and the AND gate gives us a carry of 1.
What's that? It's 1, 0, which in binary is the number 2. These gates just added 1 plus 1.
And this is the true power of scaling things up. Your computer's processor has what's called an arithmetic logic unit, or ALU, and it's basically billions of these simple little adder circuits all chained together. And that is how it performs every single calculation you can imagine.
So these rules aren't just baked into our hardware, they are absolutely everywhere in our software. From deciding how much you pay for a movie ticket to, well, causing other pretty famous catastrophes. Here's a super simple everyday example. A movie theater wants to give a discount to kids and to seniors. The logic in the code is a direct translation of our OR gate. If your age is less than 16 or it's greater than 65, that condition becomes true, and boom, you get the discount. Simple, effective, and all powered by Boolean logic. But what happens when the logic is just a little bit flawed in a slightly more expensive project? In 1996, the Ariane 5 rocket exploded just 37 seconds after liftoff. And the cause? It wasn't mechanical. It was a logical failure, a data error. The specific problem was something called an overflow error. Basically, the rocket's guidance system tried to stuff a big 64-bit number into a tiny 16-bit space. It's like trying to pour a whole gallon of water into a coffee cup. It just doesn't fit. The system couldn't handle it, the data got corrupted, and the rocket's logic sent it flying off course. A simple boundary check, another logical test, could have prevented the whole thing. And that brings us right back to where we started. From a nationwide internet outage to an exploding rocket, these aren't just technical glitches. They're failures of clear, structured thinking. Understanding this logic isn't just for programmers. It's a superpower for reliability, no matter what you do. At the end of the day, Boolean logic isn't really just about ones and zeros. It's a framework for building dependable systems, for asking the right questions, and for thinking through all the possible outcomes. So I'm going to leave you with a question to ponder. Where in your life, or in your work, could a little bit of clear, logical thinking, maybe a simple truth table, save you from your own Friday outage moment?